The next time your plane hits turbulence, forget the wings. Worry about the microscopic piece of rock inside the flight computer, because if that rock bends by even a fraction of a millimeter, your 300-ton metal tube effectively goes completely blind in the sky. Deep inside the avionics, modern flight relies on a high-frequency sliver of quartz vibrating exactly 10 million times per second. We tend to view time as an unyielding, constant force, but the hardware we use to measure it is dangerously vulnerable to the extreme environment of flight. When a jet makes a steep climb or a sudden bank, the intense G-force doesn't just push you back in your seat, it applies immense mechanical stress to that crystal. This physical deformation actually warps the crystal's lattice structure, altering its oscillation frequency. The clock literally starts ticking at a different speed. Why does that matter? Because navigation is entirely based on time. GPS calculates your location by timing exactly how long a signal takes to arrive. If your stopwatch is broken, your map is broken. During critical maneuvers, this warping causes the clock to drift by nanoseconds. Instantly, it loses synchronization with ground-based atomic reference clocks. Now, a microsecond sounds completely harmless. But in the world of flight navigation, a discrepancy of just a few millionths of a second translates directly into hundreds of meters of positioning drift. Imagine the cascade of failures. A commercial jet hits unexpected clear air turbulence and banks hard to correct. Inside the computer, the quartz bends under the G-force. The timing slips. The GPS ghost shifts the plane's perceived location. The autopilot senses it's off course and violently corrects for an error that doesn't even exist in the physical world. Without perfect timing, modern automated landing systems and mid-air collision avoidance technology immediately become unreliable. To counteract these invisible gravitational effects, engineers had to design hardware that practically defies physics. The first line of defense is the oven-controlled crystal oscillator. It maintains a constant, baking-hot internal climate to insulate the crystal from external pressure and temperature swings. But advanced planes also use acceleration compensation systems, where built-in accelerometers feed forward a corrective electrical signal to perfectly stabilize the crystal's rhythm. To ensure absolute safety when signals fail, the military and aerospace sectors are now shifting toward chip-scale atomic clocks. How does it work? A chip-scale atomic clock traps vaporized cesium atoms within a microscopic laser grid. By measuring the exact frequency at which these atoms transition between energy states, it keeps virtually flawless time. These microatomic clocks provide assured positioning and timing entirely independently, completely bypassing the mechanical vulnerabilities of quartz. While commercial flights rely on highly stable GNSS networks, this military-grade technology represents the ultimate failsafe against the forces of physics. It's an absurd reality. Hurling a 300-ton metal tube safely through the sky relies entirely on mastering the invisible, microscopic physics of time under intense acceleration. This battle against kinetic forces isn't just a technical detail. It is a fundamental requirement for the safety of every single flight. So, every time your flight makes a smooth landing, remember it's not just a victory of aerodynamics. It is a triumph of human ingenuity over the fundamental laws of motion.